everyone. Welcome back to Ask IITians sessions. So, in the very last class of atoms and molecules, we have discussed about this chapter and we did the varied laws which are concerning or which are governing this chapter. We discussed about law of definite proportions, we discussed about conservation of mass, multiple proportions, reciprocal proportions, etc. Also, we have discussed previously about the Dalton's atomic theory, where we said that atoms were the smallest indivisible particles of nature or of matter. So today we will be discussing that very thing into deep, and these are the topics which we are going to cover in today's session. So what we're going to learn in today's session is about what is an atom, what is an atomic symbol, masses, what are the various ways in which I can write them as, and the corresponding questions. Without wasting time, let's get started. First of all, the basic question which runs in everyone's head is, what exactly is an atom? So basically, an atom by definition is the very structure of an element which cannot be further broken by any chemical means. It means it is the minutest, the tiniest, the simplest particle of any atom or any matter particle. Okay, so this is your tiniest, minutest, or you can say the simplest of all, which cannot be further broken by any chemical means whatsoever. See, so when I talk about an atom, basically what all does it have? An atom, as we've discussed before, it indeed is the smallest independently existing element or independently existing state of a substance, but it doesn't mean that we cannot further divide it into portions, or it is even composed of certain subdivisible subatomic particles, which are electrons, protons, and neutrons. As we know that these electrons are negatively charged particles. So they are the subatomic particles, or we call them as the fundamental particles of an atom. So electrons, which are negatively charged, protons, which are positively charged, and neutrons, which are chargeless. Now, these are the basic 3 units of an atom. Doesn't mean that these are the only ones. We do have more. We have quarks, we have mesons, we have neutrinos, antineutrinos. We have loads of them. But these are the most important and the major ones. Now, it is the neutron and the proton which together is known as nucleon. That means the resident of the nucleus. So it means that actually we have a model of arranging these subatomic particles in an atom. And that model we call as the planetary model. We call that model as the planetary model. As per this model, as you know about the entire solar system, right? So there is sun, and then all the planets revolve around it. So as per this model, there is a central heavy body, which is known as the nucleus, around which all the electrons revolve. And it is this central body, which is the nucleus, which contains your protons and neutrons. So this is the model that we have for any atom. Right, Bacha? Now, whenever we have these atoms, basically, we can just represent them in a particular manner. We just represent them in a particular way, in a particular manner. What is the manner? So, see, I think you, like many of you, might have seen a particular chart which is known as the modern periodic table, which looks something like this. Some of you might be even having it as a chart at their house. Some people who are actually chemistry lovers or are highly afraid of chemistry. This is just to have a view of it every now and then. So this is how your periodic table looks like. This is just like a fort. Okay. So in this, if you see the periodic table, all the elements which have been discovered, no, I won't say the ones which have been discovered because there are many elements which are yet to be discovered. When this periodic table was first formed, by then we knew 118 elements by then. So this periodic table covers all those 118 elements, but now there have been more which have been found out. But if you talk about the elements which they have already inserted in this periodic table, so it is represented in this form. Where what do we write? We write the symbol of that element first. Now, previously we had pictorial representations of the symbols of the elements. Okay, but then it is very difficult to remember all the pictorial things. If you know one of the ancient languages, which is Hebrew language, is all about pictorial representations. If you have seen the mummy or the mummy returns, they have used that symbology. Okay. But then it is not easy to remember what a pigeon signifies, right? Or over here, what does a triangle signify? What do you mean by a solid sphere or a hollow sphere? These were the symbols previously. See, it's very difficult to remember. So what the scientists did, and it's an amazing thing that they did, that is they used the English terminologies for the elements and took either the first letter or the first two letters or the first and third letter to write their symbols. For instance, if I talk about hydrogen, so the symbol of hydrogen is H. Same way, even helium starts with H. Now, you cannot give the same alphabet to two different elements, otherwise it will create commotion. So what we did, we took the first two alphabets, H. Now it becomes an easy thing. Same way, if I talk about oxygen, it starts with O. So we used O as the symbol. There's another element which is osmium, again starting with O. I did the wrong spelling. Yeah. So now what will I do? I'll take the first two alphabets. But not every element is taken by their English terms. Some elements, symbols are taken from their Latin terms. For instance, if I talk about sodium, so sodium is natrium in Latin, and therefore the symbol is Na. Same way, potassium, its name in Latin is kalium. So you took K from that. So this is how we got the symbols of the elements. Now, in these symbols, we do two things. We use subscript and superscript to define certain things about these elements. So I use the subscript, which is atomic number, and the superscript, which is your mass number. This atomic number is represented by the symbol Z, whereas the mass number is represented by the symbol A. Now the question is, what do these terms signify? See, atomic number is a term which signifies the total number of protons present in an element. Total number of protons which are present in an element. Now you see that when you talk about protons, right? So if I talk about any element, we always talk about neutral elements, right? So if your atom, or if you have a neutral element, then the number of protons will be equal to the number of electrons also. So this gives me the entire information about the total number of protons and electrons present in a neutral element. All right, so I understood what is atomic number. Now what is mass number? So mass number is basically a number which tries to tell about the mass of that element. The mass of that element. Now, your total mass is contributed by the total number of protons and neutrons. Sorry, protons and neutrons, as you'll be doing in the next chapter, structure of atom, they both are relatively higher species. Relatively higher species as in higher molecular mass species as in, if you talk about the mass of a proton, so it is 1.64 into 10 to the power of minus 27 kgs. Whereas the mass of the electron is only 9.1 into 10 to the power of minus 31 kgs. So if you see the difference, it has a difference of nearly 1000 kgs. Nearly 1000 kgs. So I have not used this part. Okay. I'm only talking with respect to this. If you do the actual calculation of that ratio, then you'll find that electron is precisely 1847 times lighter as compared to the proton. 1800 times lighter, which means its mass is just like the mass of an ant over an elephant, which is so low. So it doesn't matter even if you consider that mass in the total mass of the elephant or not. The mass of the ant, even if you can ignore, if you want, you can easily ignore, because it's relatively very, very low in comparison to the mass of the overall species, right? Make sense? So, but if you see the mass of the neutron is 1.67 into 10 to the power of minus 27 kgs, which is in similar zone as to that of the mass of the proton. So since they both are heavier species, so they are the ones which contribute to the overall mass of an atom. Therefore, the mass number simply represents the total, the sum total of protons plus neutrons, right? So if you'll see here, see in this very case, how will I represent oxygen then? So below I'll write 8 and over I'll write 16. 15.9999 is 16. And what is AMU? AMU represents atomic mass unit. It's a very specific unit. Why a specific unit? That's because if you see that the atom is very, very small. It cannot be seen with any naked eye. Since the atom is very small, you cannot actually find out its mass just like that. So what do? We find its relative mass. And for finding out even the relative mass, I would be needing some unit to justify that mass. Since the masses are very low, we have devised a very specific unit for or to represent the mass of an atom, and we call that unit as atomic mass unit. Okay, but just for your information, atomic mass unit is a gone scenario now. It's no longer used. So what you have done is we have moved to another unit for mass, and that is your unified mass. So the new unit for the mass of an atom is unified mass, represented by U. Only U. Right? Are we clear up till here? Okay then. So now let's talk about another part. So if you say about the mass number, okay, so what happens is mass number or A is equal to what? The total number of protons plus the total neutrons. Now, total protons are also given by the atomic number, that is Z, plus the number of neutrons, which means by using this equation, I can easily find out the total number of protons, electrons, and neutrons in any given system. Right? Make sense? Right. Okay. So, for instance, if I talk about it, I'll take an example of oxygen. So, in oxygen, what happens? There are 8 protons because the atomic number is 8, right? And how many total mass is there? Total mass is 60, right? So, if I'll talk about oxygen, the value of A is 60 and the total protons is 8 because of the atomic number. So if I'll solve this equation, what is the value of N that we are getting? Quickly tell me. Right. The answer would be 8. So from here, I'll get the value of N as 8, which means that the total number of neutrons which are found in an oxygen atom will be 8, which also suggests that the number of protons, electrons, and neutrons in a neutral atom of oxygen will be 8. Right? Make sense? Okay then. So let's move to another portion. And the next portion that we have to discuss is the atomic mass. See, atomic mass, as we have just discussed, is the mass of the atom, which is comprised of the mass of electrons, neutrons, and protons, majorly. Right? Now, when you talk about these masses, we've just discussed that the neutrons and protons contribute more towards the mass of an atom as compared to the electrons. Electrons just contribute negligibly. That doesn't mean that they don't contribute at all. That their mass contribution is negligible. Right? Now, but you've seen that the numbers, like just in the previous example, you saw something which is 15.9 now. Now, how can something be 15.99? Because if it is actually the sum total of neutrons and protons, then how can it be a fraction? It's not possible. You cannot have half a neutron or a quarter of a proton. That's not possible. So then why am I getting that way? So the answer lies in something known as the relative molecular mass. The relative mass. So when I talk about the relative mass, or you call it as average mass, so what exactly is that? That is basically the average mass of your isotopes. That's basically the average mass of the isotopes. Now see what happens. If you talk about which example should I take? Okay, let's take it this way. You remember, right? We were talking about the Dalton's atomic theory, right? So in Dalton's atomic theory, we discussed that it's not mandatory that the elements having like the same elements should have all the properties the same and the masses should be same. It's not mandatory. And the reason was the presence of isotopes. So isotopes are the ones with the same atomic number but different mass number. These are the elements with same atomic number but different mass number. Now, when I talk about the difference in mass numbers, so what happens? What problem does it create? It creates a problem with the relative availability of an element. Okay, so we talk about the relative availability. So you see that if I talk about chlorine, okay, so chlorine is present in two isotopic forms. Chlorine, if I talk about the element, will have the same atomic number, which is 70. But different mass numbers, since I'm talking about the allotropes of chlorine. So you get chlorines with two isotopes, one with a mass number of 35 and another one with a mass number of 37. Now, these two isotopes are found deeply in nature where the distribution of these elements is not homogeneous. Okay, so it's not evenly distributed in this world. Now, evenly or unevenly means it means that you in the world, when you try to dig out chlorine, we found that it is the 35 chlorine which is found in major quantities. So the out of the total chlorine that we have extracted from nature, 75% of it is 35 chlorine and only 25% of it is 37 chlorine. Okay. So that is their relative abundance. After knowing the relative abundance, I know that one mass will not be sufficient or the right thing to tell the entire mass of chlorine atom. Right? It's not the right way to design it because see, both of them are contributing. So both should be given equal respect. In that case, we come to another conclusion, and that is related to the average mass. Now, how do I find out the average mass? So the way is very simple. What you need to do is we need to find out the relative abundance. Okay, so basically, relative abundance or their percentages is the same thing. So this is your relative abundance of one isotope multiplied by the mass of that isotope. Plus, again, the relative abundance of second isotope multiplied by the mass of the second isotope and divided by total abundance. So total abundance will be 100, 75% plus 25%. Okay. So what I'll do is I'll just start solving it. So relative abundance is 75 for a mass of 35, and it is 25% for chlorine with a mass of 37, where the total abundance is 100. So when you solve it, you'll find that the average mass turns out to be 35.5. Now, it is very difficult to actually explain it with the help of the mass number, because technically the mass numbers cannot be 0.5s or fractions or decimals. That's not possible. But if you find out this way, that yes, it is justified manner, that okay, yes, the masses can be in fractions using this entire concept. I hope the things are clear up till here. I wish that. Yeah. If yes, then let's move forward and we'll talk about the next part. All right. So we'll talk about the thing which is known as the gram atomic mass. Right. So gram atomic mass basically talks about, and it is the mass of an element in grams. That's it. So whatever is the mass number, you just put grams afterwards. Instead of the units being AMU or U, just put it grams. And the mass will become the mass of the gram atomic mass. Okay. All right. See, one second, Bacha. All right, everyone, welcome back. All right, so let's get started. So, what were we discussing? We were talking about the. Okay, students. So, you understood that gram atomic mass simply refers to the mass or the mass number of an element with the units being gram. Right? Now, technically, what is that? So technically, if I talk about the gram atomic mass or the gram atomic weight, it is the mass of Avogadro number of particles of atoms. See, you know that one, two atoms, they are very small, cannot be seen with the naked eyes. You cannot even have a justifiable mass of theirs, right? So you need a bulk quantity so that at least they can be weighed on a weighing balance. So, to know the exact quantity or to know the exact number, of those many particles which I should be taking, Mr. Avogadro did an amazing work. And from there, he found out that if I take Avogadro number of particles, which is 6.022 into 10 to the power of 23 particles, 6.022 into 10 to the power of 23 particles, then that represents the mass of that particle in grams. Then that represents the mass of that particle in grams. Which means if the particle is atom, so I will get the mass of the atom in grams. Okay, for instance, if I take carbon, so in the case of carbon is having atoms. So if I have 6.022 into 10 to the power of 23 atoms of carbon, then it will have a total mass of 12 grams. So since it is the mass of an atom in grams, therefore we call it as gram atomic mass. Same way, instead, if my particle is a molecule, right, in that case, if I'll give the mass in grams, I'll be calling it as gram molecular mass. It is this gram atomic mass or gram molecular mass which is also known as mole, which is again a quantity, a unit of quantity, about which we'll be understanding in our upcoming lectures. Also, because it's like such a big number to write every time, right? So we have a very simple shortcut for it, and the shortcut is this number is represented as Na or N naught, Avogadro's number, right? So this is like the simple thing. About molecular mass, we will be discussing, so don't worry. We will be discussing that. So this was majorly about the atomic mass. That is the mass of an atom. Same way, if I talk about the mass of oxygen, so if I have Avogadro number of atoms of oxygen, we just did its mass number is 8. So it will have 8 grams. And 8 grams will be the gram atomic mass of it, which means it is the mass of 1 mole of oxygen atoms. Right? I hope I'm clear up today. This is a very, very easy stuff. If you're getting it in one go, just don't be surprised. It is a very easy thing. So just don't worry. All right. So now we come to another thing which is known as the molecule. So the thing which we just talked about, but the question is, what exactly is a molecule? So technically, a molecule is defined as 2 or more atoms of the same element or different elements which are bound together. 2 or more atoms. Okay. So when, suppose you talk about hydrogen, right? Hydrogen gas is represented as H2. It means I'm having 2 atoms of hydrogen which are connected together. 2 different atoms of hydrogen which are now connected together. So this is your hydrogen molecule. Whereas these were atoms of hydrogen. Same way, we can have ozone, right? So ozone is composed of 3 atoms. Okay. So there are 3 atoms of oxygen which have compiled together to give you a molecule which is ozone. This is your ozone molecule. Now, these were the examples of molecule in which there was same type of atom. What if we have different type of atoms? For instance, we're given with an example here, water. So I can have in the water part, there can be 2 hydrogen atoms and 1 oxygen atom. So when they compile together, there are 2 H's and 1 O, which has fused together. Now this is your water molecule, right? This one is your water molecule. So your molecules can be comprised of the same element or different elements, right? Make sense? So we have many examples for molecules. For example, we have carbon dioxide, we have ammonia, we have sulfuric acid, we have nitric acid, we have sodium hydroxide, etc. Which are having different types of atoms. Okay? And the total number of atoms which are contained in a molecule, that is known as atomicity. Atomicity means the number of atoms present in a molecule. For instance, if I talk about carbon dioxide, it will be 3. Ammonia, so there are 1 nitrogen atom, 3 hydrogen atoms, total 4 atoms. Sulfuric acid, 2 hydrogen atoms plus 1 sulfur plus 4 oxygens. So total atoms present in sulfuric, 1 molecule of sulfuric acid is 7. So its atomicity is 7. So this is what we mean by atomicity. Different molecules have different atomicities, right? Now we talk about something which is known as the molecular mass. Okay. So when I talk about the molecular mass, that is defined for an atom as the sum total of the masses of each and every element. It is defined as the sum of the masses of each element. For instance, as they have given here as an example, if I talk about water, right? So in water, what is happening? You have, water is basically H2O. So in water molecule, you have 2 atoms of hydrogen and 1 of oxygen. So I'll just add the sum of all the atoms. What is the sum? 1 hydrogen atom is having a mass number of 1, whereas oxygen has a mass number of 16. Right? So if I add the sum, so there's contribution of 16 mass from 1 oxygen atom and 2 from hydrogens. So there is 1 hydrogen is having a mass of 1 U and 1 oxygen atom is having a mass of 16 U. So total mass of water is 18 U. And that 18 U refers to the mass of 1 molecule of water. Right? Same way, if I take another example of ammonia. So ammonia is composed of nitrogen plus 3 hydrogens. So the mass of 1 nitrogen atom is 14 U and the mass of 1 hydrogen atom is 1 U. Since there are total 3 So this is the mass contribution by hydrogen. Total contribution is 17. This refers to the mass of one molecule of ammonia. Right? From there, just remember, I think somewhere we have just used the mass of oxygen as 8. Oh, yeah, here. So you see the mass of oxygen atom is 60. By chance, I wrote it. I just changed the answer. Okay. Now, I'll come back again to another thing which is known as the gram molecular mass. As we have discussed before, gram molecular mass is basically the mass of 1 mole of a substance in grams. Just now we discussed what is 1 mole. 1 mole refers to Avogadro number of particles. And this time the particles will be molecules. So this is the mass in grams of Avogadro number of molecules, which means the mass of 6.022 into 10 to the power of 23 molecules present of the same type. For instance, if I talk about 1 mole of water. So 1 mole of water would mean I'm having Avogadro number of particles of water. Right? Now, you know that the mass of 1 molecule of water is 18U. So Avogadro number of particles would be Avogadro number of particles into 18U. So that will give you always the same number with the units being gram. So as per the definitions, gram molecular mass simply refers to the mass of a substance in grams. Right? So 1 mole of water means Avogadro number of particles of water, which means 18 grams of water. Same way, if I talk about 1 mole of ammonia, it means the total mass of Avogadro number of particles or molecules of ammonia. So this mass, I'll be writing it as the number would be as it is, as equal to the molecular mass which we just found, and the units will simply change to grams. And it is from here that we call it as GMM, or the gram molecular mass, which is nothing else but another term for moles. Whether you talk about gram atomic mass or gram molecular mass, these are just another terms for moles. Right? Now, I'll talk about another case, that is formula mass. Okay. Formula mass. So now when I talk about that, see. Formula mass is basically a mass which is defined for ions. The mass which is defined for ions. So formula mass of a substance is the sum of the average atomic masses of each ion represented in the chemical formula. Okay. But of course, see, whenever you talk about any molecule, right? So for every molecule, it's not about the ions in which we write it. We don't write everything in terms of ions every time. Okay, but if I won't say that, you'll find, or you might be scratching your heads and would be asking yourself a question that why do we have a different term as molecular mass and formula mass if both of the things are representing the same thing? Right? So it is because of that reason I have changed it to ions. Now, This is valid for any substance which in itself is an ionic compound. It is valid for every single substance which is an ionic compound. Now, about ionic compounds, we will be discussing it in detail in 10th grade under the chapter of metals and nonmetals. So it's a pure thing about ionic compounds. But otherwise, I'll just give you a briefing about it. So when I talk about ionic compounds, basically, so they are the ones which are formed from your group 1 and group 2 metals. What is a group 1 and group 2 metal? So basically, when you talk about your strong metals like lithium, potassium, sodium, calcium, magnesium, these metals, along with strong non-metals. Okay, so group 1 and 2 comes from your periodic classification. It comes from um, uh, periodic classification. That group, what is group 1 and group 2. So you remember the fort which I made? The first two lines, like vertical columns, represents group 1 and group 2. The last few represents, the last one is basically 18. So just one before it is group 17. So your group 17 elements majorly, these are your strong non-metals by the name of fluorine, chlorine, bromine, iodine. And these non-metals are known as halogens. So that is fluorine, chlorine, bromine, iodine. All right. So when I talk about these elements, what happens? If I talk about one molecule of NaCl, okay, so one molecule of NaCl is composed of one Na and one Cl. Okay. One Na and one Cl. Now, if I talk about the mass of one Na, so the mass of one sodium is basically 23, whereas the mass of one chlorine atom is 35.5. We just calculated, right? So if I add the two, we'll find the total mass of it as 58.5. So the mass, this is the mass of one molecule of sodium chloride. Now, you could have directly said it as the molecular mass. It wouldn't have made any difference. It's just a different term which we use for ionic compounds. So it's basically the same as the molecular mass with a twist on the name, and that is we have kept the name as formula mass. Okay, we've just twisted the name as formula mass. Same way, when I talk about this formula mass, this is the mass of one molecule. What if I have Avogadro number of molecules? So then, as per the simple terminology, we just keep the same mass and the units being grams. So it's 58.5 grams this time. And previously we used to call it as gram atomic mass or gram molecular mass. This time we are going to call it as gram formula mass, which is GFM, just another term for mole. So this is the mass of 1 mole of sodium chloride, right? Clear? Well, that's wonderful. So just, it's just another term for molecular mass. There's no change in it. Okay. So let's see some questions which are based on this. So that completes my theory, and now we'll come to some questions. So the question is, why is it not possible to see an atom with naked eyes? Oh, such an easy question. So, first reason is they're very, very minute in nature. And our resolution of eye is not that very keen. Okay. So, it's not that low. So, that is why we cannot go to that level. Okay. And since it is very, very small, hence our eyes cannot identify them. These atoms are measured in nanometers, which is even the wavelength of light. So our eyes cannot see that. All right. Now, we have a second reason too. So what is the second reason? So the second reason is that except for the atoms of noble gases. Okay, now what is a noble gas? So noble gases are highly stable gases, okay, which are a part of group 18 in the periodic table. For example, our noble gases are helium, argon, krypton, etc. So the atoms of noble gases exist independently. But if you talk about every other case, they don't exist independently. Okay, but they are talking about the non-metals because even the atoms of metals exist independently. So therefore, we cannot, since something is not even existing independently, how can we have or how can we see it with our naked eyes independently? So you cannot see them, the atoms. Okay, so we just have noble gases which are independently existing, and the worst part is you cannot see air. You cannot see any gas. So we cannot see the atoms, right? Okay, so that was about this question. Now let's talk about the next question, which is what is meant by the term chemical formula? Now, this is an important question. What do you understand by this term chemical formula? So, chemical formula is nothing else but a symbolic representation of any chemical compound. Now, what is a symbolic representation? Symbolic representation means the number and the type or the kinds of atoms which are present in one molecule of a substance. Okay, chemical formula is just a symbolic representation of the number of atoms which are present in it and the type of atoms present in it. For instance, if I talk about hydrochloric acid, so hydrochloric acid is HCl. It means that one molecule of hydrochloric acid is composed of one hydrogen atom and one chlorine atom. One hydrogen atom, one chlorine atom. Same way, if I talk about water, so instead of writing water every time, I'll simply write H2O, which is nothing else but a chemical formula of water, which is representing that water is composed of two parts of hydrogen and one part of oxygen. Right? Easy. Same way, if I talk about ammonia, it will be, that's correct, NH3, which represents that it is composed of one part of nitrogen and three parts of hydrogen. So that is the very basic part about atoms and molecules, and that's all from my end. In the next class, we will be discussing about this chapter in greater detail, and I'll be talking more about the mole concept. So stay tuned and keep connected. Bye-bye. Take care.